Hello there. In this lesson, we are going to continue studying the calculation of complex areas. In fact, what we are going to study is the same problem that we saw in the previous video, but in this case, we will address the problem in a completely different way, in a more creative one. Let's remember that the problem was to calculate the area determined between these three lines. Put it differently, between the line x plus y equals 2, between the line y equals 2, and between the parabola x squared. In addition to this information, we also need to specify which of the three bounded regions is the one that we are interested in. In this case, the relevant one contains the point 0, 1. Well, in order to calculate said area, we could proceed as we did in the previous lesson by dividing that region into two pieces, then calculating A1 and A2 and combining the area of them both. However, a slightly more creative approach towards the integral calculation would allow us to calculate the same area in the following way. Let's get started by doing some observations. First, let's notice that the line x plus y equals 2 is actually making a cut, and that if we draw a vertical line from the meeting point, 1, 1 upwards, we see that what we are actually removing is a little triangle, and we do know that triangles' areas can be calculated directly, without the need of integral calculation. In this case, we are talking about a triangle that has 1 as its base and height, and therefore its area would be its base multiplied by its height, that is to say, 1 multiplied by 1 and divided by 2, which equals 1 divided by 2. Therefore, the area of that triangle is 1 divided by 2, and therefore we know how much that small region is worth. Furthermore, when we focus on the red highlighted area below the line x squared, we see that this one just so happens to be a simple integral. It is the area that is left between the line x squared and the line y equals 0. To clarify, it is integrated between the meeting points, which, as we said earlier, are minus the square root of 2 and 1. That would be a single very straightforward integral instead of 2. It is the integral that would give us the area of the red region. Well, having said that, let's notice that the region highlighted with red below and the small triangle above combined with the region that we actually want to calculate. In other words, region A gives us exactly a rectangular shape. A rectangle whose height and base we already know. Therefore, calculating the area of such a rectangle is very simple. Base multiplied by height. Let's do that then. We multiply its base by its height, the base being the squared root of 2 plus 1, and then we multiply it by its height, which happens to be exactly 2. That would basically be the area of the main rectangle. Now, to that rectangle, we should remove the small two pieces that we had highlighted before with red. On one hand, the triangle that we said had an area equal to 1 divided by 2, and on the other hand, the region that is below in red, which is the integral between minus squared root of 2 and 1 of the function x squared. We have reduced our problem to calculate a single integral, in which the integrand is also very simple. Therefore, the result will come out more smoothly. This way of using integral calculation is way more creative overall. In this case, in a direct way, by doing the first calculation and simplifying the first two terms, we obtain the 3 plus 4 multiplied by the square root of 2 divided by 2. Next, we move on to the second integral, which we must remember is equivalent to finding its primitive. In this case, the antiderivative is x cubed divided by 3. We apply Barrow's rule with the integration limits of 1 and minus the square root of 2. When we do this, we obtain the result of 1 plus 2 times the square root of 2 divided by 3. If we unify both fractions, as we well know how to do, what we obtain is 8 multiplied by the square root of 2 plus 7 divided by 6. Well, so this is the exercise so far. Today we have seen how the actual calculation of integrals and areas does not have to be a fixed method and leaves plenty of room for freedom, creativity, and diverse perspectives. I am really hoping that this example truly helps you break free from the notion that integrals must always be approached in a strict, predefined manner. Mathematics, like many other things in life, isn't solely black or white. It allows for a spectrum of possibilities and interpretations.